Hi, this is Dave Johnson with another edition of Math Off Topics. Uh, Today we're going to talk about uh, the comparison between the Squeeze theorem and the Zero-Bounded Limit Theorem. In previous videos, I talked about the Squeeze theorem, and I also talked about in another video the Zero-Bounded Limit Theorem. Those are two methods that are used to evaluate limits. Uh, I've also talked about other ways of evaluating limits, including the conjugate methods, uh, the square root conjugate, this cube root conjugate, and what might be called the trigonometric conjugate method. So let's get into it. I have a specific example that I have in mind. So limit as x goes to 0 of x sine 1 over x. Now, if you look at this, you think, well, x is 0. If you just set x equal to 0, then and what is sine of 1 over x? Well, that's undefined, but what's the limit of that? Turns out that limit is undefined, so you cannot treat this as a product of limits. In other words, one of the methods for evaluating limits is to say, well, the limit of a product is the product of the limits. But in this case, the x, say if we said, in fact, let's go ahead and write it. If we wrote this as limit as x goes to 0 of x times the limit as x goes to 0 of sine 1 over x, you're not allowed to do this because although this is 0, this does not exist. And when that limit does not exist, you're not allowed to use that limit theorem. Now, you may say, well, wait a minute, it gives you the right answer. No, from a logical standpoint, if the theorem doesn't apply, if the limit property doesn't apply, then you're not allowed to do this. So we can't use this method. So I'm just going to cross this out. Okay, not legal. So instead, let's choose between the zero-bounded limit theorem and the squeeze theorem. And let's do the zero-bounded limit theorem first. So zero-bounded limit theorem. And let's treat the bounded function as sine of 1 over x. So b of x is equal to sine 1 over x. And I say that because sine of 1 over x is bounded between -1 and 1. And remember, if you go back and look at that video, the zero-bounded limit theorem doesn't say anything about whether the limit exists for the bounded function. It doesn't say anything about the limit at all for the bounded function. It only has to be bounded, okay? So, and then the other function, which we called g of x, that's x, and so its limit is 0. And so we can say the limit as x goes to 0 of g of x is equal to 0. And because of that, we can conclude that the limit as x goes to 0 of g of x, which is x, times the bounded function sine of 1 over x, that has to be 0 also. So that's our answer, and it's that easy. Now you got to be a little careful. Your teacher may not want you to use the zero-bounded limit theorem, so you should probably have a conversation with your teacher to make sure that that would be legal. Also, it's a good idea to reference the theorem, say in a homework problem or on an exam problem, just say, I'm using the zero-bounded limit theorem. And then if your teacher has allowed you to use it, then you're on firm ground. Otherwise, you may get points taken off. And I would hate to be responsible for that. So make sure you talk to your teacher about this. The other possibility is to do it with the squeeze theorem. which is often the one that the teacher wants you to use. So let's say Squeeze Theorem. And if you watch the other video that I did, it says that as long as you have an inequality, f of x less than or equal to, let me just go ahead and write that down, f of x less than or equal to g of x less than or equal to h of x, if you can find an inequality for which that's true, and if the limit as, say, x approaches a of f of x is equal to the limit as x approaches a of h of x, and those are equal to the same limit, call it L, then, so if these statements are true, then the limit of the middle function, so limit as x approaches a of g of x, is also equal to L. So the problem now becomes one of finding a legal correct inequality. So, and we want g of x in this case to be the x sine 1 over x. So as I showed you in the other video, if it's a common practice to say, okay, let's take sine of 1 over x and write that between -1 and 1, because the sine function, its range is -1 to 1. Okay, great. Well, if we multiply, so we have to be careful here, because if we multiply both sides by x, x can be negative. So we have to treat two different cases, x greater than 0 and x less than 0, and make sure that we come up with a legal correct inequality that we can use for our squeeze theorem. So let's say case 1, x greater than 0. And so if I do that, multiply both sides of the inequality by x, now because x is positive, I don't have to change the direction of the inequality. So we get negative x less than or equal to x sine 1 over x less than or equal to x times 1 is x. Okay, so far so good. But we have to be, again, careful here, because this is only true for x greater than 0. We need something that's going to be true for both x greater than 0 and x less than 0. And there are a variety of ways of doing this, but I think the easiest way to do this is to think about rewriting the negative x on the left and the positive x on the right in terms of the absolute value function. And you'll see in a minute why we're going to do that. So let's remind ourselves. So the absolute value of x is equal to a piecewise defined function. It's equal to x if x is greater than 0, and it's equal to negative x if x is less than 0. Okay, well, but we have x is greater than 0. So let me do this in red, and let's consider this part of the piecewise defined function. And so if that's the case, then for our case 1, the absolute value of x is equal to x. And so everywhere I see an x, at least on the outside of the inequality, I'm going to replace it with the absolute value of x. I don't want to replace this one, because then I would be changing the function that I want to find the limit of. So I'm only going to substitute for this part here and this part here. So if we do that, the x is the absolute value of x, so therefore, let me write this in black. So negative x would be the negative of the absolute value of x, and then that's less than or equal to x sine 1 over x. And that's also less than or equal to x, which we are saying is equal to the absolute value of x. And this is true because x is greater than 0. Okay, so far so good. Okay, so let's do case 2. Let me write that down. So case 2, x less than 0, and we're going to start here now and multiply both sides by x, but x is negative, and because it's an absolute or an inequality, we have to change the direction of the inequality, and we do that. So we get the negative times x, so we get negative x greater than or equal to x sine 1 over x greater than or equal to, and then this 1 times x, which is x. Okay. And we had to do that because the inequality, if you multiply both sides of that by a negative number, you have to change the direction of the inequality. But we don't want the greater than or equal to's in there. We want them to be less than or equal to's. So we can switch the positions of everything, swap it around, and so the right side becomes the left side. So x less than or equal to, and then x sine 1 over x doesn't change, and then less than or equal to the negative x. So this part came over here, and this part came over here when we changed the direction of the inequality. Okay. Now we're getting closer, but we still have to figure out how to get the absolute values in there. So this time let's look at the bottom branch of the piecewise defined function. And so negative x becomes, and I can write it in red here. So this becomes the absolute value of x. The middle part stays the same, so x sine 1 over x. And then the x, so if negative x is equal to the absolute value of x, then it must be the case that x is equal to the negative of the absolute value of x. And so I can replace this with the negative absolute value of x. And notice now, the result of case 2 is the same as the result of case 1. Case 1 was x greater than 0. Case 2 is x less than 0. And so we can combine them into a single result. So let me do that. So I can just write this now as negative absolute value of x less than or equal to x sine 1 over x less than or equal to absolute value of x. Now we can apply the squeeze theorem because we have a valid, correct, logical inequality that we've derived with some effort. But the limit of this is going to be 0. The limit of this is 0. And so therefore, the limit as x approaches 0 of x sine 1 over x is equal to 0. Now, I want to point out that the effort that it took to do the squeeze theorem part of it was more because we had to construct the inequality. And that is sometimes the case. Whereas doing the same problem with the zero-bounded limit theorem was very easy. But again, I want to emphasize that the zero-bounded limit theorem is a special case of the squeeze theorem and doesn't always apply. And so be careful. You can't just go around replacing every occurrence of the squeeze theorem with the zero-bounded limit theorem. And so I hope that's been helpful. If you've enjoyed this video and found it helpful, please like and subscribe, and I will see you next time.